This is the third part of the lecture on integral calculus. We will start by stating some very simple but useful properties of definite integrals. The first property states that suppose we have uh, an interval a to c and we want to find out the area under the curve, then we know from before that we simply have to take the integral of a to c. Now here what we are saying is that suppose we have a point B which lies between A and C. In that case, the area under the curve A to B and B to C, we can simply add them up to get the area under A to C. So this can be written as that integral of A to C is equal to integral of A to B plus integral of B to C. This is the proof, very intuitive proof, which you should be able to follow. Left hand side is equal to, this is the left hand side, FC minus FA. Right hand side is this is FB minus FA, and this is FC minus FB. The FB cancels out, so we have FC minus FA. This is the second property. If we integrate from A to A, then which is identical to that we are integrating from A to C, C tends to A, then the area will be 0. So the proof is again very obvious. FA minus FA equal to 0. If you consider the right hand side, the limit C to A, you can see that this is FC minus FA, and if you put C to A, then this becomes FA. FA minus FA is equal to 0. The third property is that if we reverse the direction of integral, this will change the sign of the integral. So we have integral of A to C. Instead of that, if we write C to A, then we have to put a minus before that. Again, this is intuitive. A to C means FC minus FA. We simply take the minus common, so it becomes FA minus FC. So this is minus into C to A. So up till now, we have been treating the integral A to C fx dx as the area beneath the curve fx and implicitly above the horizontal or x-axis. However, if a function is negative value, like in this case, then the integral is the area between this function and the x-axis. So it is the area above the function and below the x-axis. But this area has to be measured as a negative value. So we can see we are integrating from 0 to 2, and the function is minus 2x minus 1. So this will be x square minus x. And now if we substitute the values of 2 and 0, we will get over here minus 4 minus 2, so it's minus 6, and this is 0, so we get minus 6. Property 4 is that suppose we have a function which is negatively valued in the interval a to c, then this integral will be, the area will be negative. So an economic application of this property is that suppose we are tracing the investment of a firm from a period A to T. Now in some subintervals, we have a positive net investment, and in some cases the depreciation is greater. We have only depreciation, so that we have negative net investment. For instance, in this period, we have a positive investment A1, A3, A5, but in the second and fourth subperiod, the net investment A2 and A4 are negative. So here we simply have to sum up all the areas. So A1 plus A2 plus A3 plus A4 plus A5, keeping in mind that A2 and A4 are negative and A1, A3 and A5 are positive. So we write this as integral of A to C is A to B1, which is positive, plus B1 to B2, this will be negative, plus B2 to B3, positive, B3 to B4, this is again negative, and finally B4 to C. So the net investment is given by this formula. Now we are going to discuss consumer surplus. Consumer surplus can be defined as follows. Let's suppose we have a demand curve and the price is P star at which Q star is sold. Now, if we have, this should be Q1, not Q2. So suppose the price increases to P1. In that case, the demand will be Q1. If price increases to P2, demand will be Q1. Okay. Now, the point that we want to make is that suppose for the amount Q1, the consumer was, for the amount Q2, the consumer was willing to pay a price higher than the market price, P1. For the amount Q2, the consumer was willing to pay a price higher than the market price, P2. So, when the consumer buys all the product at P star, then he's basically making a savings. So this saving is given by this length, the gap between the demand curve and the equilibrium price, the market price. So for Q2, this is the savings that the consumer makes. For Q1, this is what the consumer saves. This is what we call consumer surplus. So if we sum up for the area, for the boundary 0 to Q star, we will get a large number of such lines, and more simply, this triangle is the consumer surplus. So the consumer surplus is the area between the demand curve and above the market price. We can find it out in two ways. First is using the integral. This is the area under the demand curve, and we simply subtract this rectangle P star into Q star. So we will get this area, consumer surplus. In case of producer surplus, this is the supply curve, which you know in perfect computation is the marginal cost curve. The market price is P star, but the consumer is willing to offer lower prices. For Q2, he is willing to sell at P2. For Q1, he is willing to accept a price of P1. So in this case, what the consumer does is, what the producer does is, he makes a saving. He makes a profit. This profit is, you can see the area below P star. It's basically P star minus P1, which is given by this blue line. Here again, it's P star minus P2. So if we take the interval 0 to Q star, it is the area between P star and above the supply curve, this triangle. So now if you want to find out what the producer surplus is, we simply take the rectangle P star into Q star, and then we subtract this triangle. So this is the integral of the function from 0 to Q star. So if we subtract, we get this as the producer surplus. We now will go to a more technical discussion of consumer and producer surplus.